Okay, hello everybody. I'm here today to talk to you about TLS. My name's Marcus Bointon. I have a little two-man company that's based in the UK, though I actually live in France. That doesn't have a great future, I think, this combination. But there we go. You've probably used my code at some point because I'm the maintainer of PHP Mailer, which more or less the entire world has used at some point. If you were in IPC Munich last year, I did a keynote there all about that because it has quite an interesting story behind it. I've got a long history behind the smartmessages.net product, which is an email marketing system. And as part of that, I've had to do lots of security, TLS, privacy stuff. So I've become something of a privacy advocate as well. And I'm doing a talk on that tomorrow. So first up, what is TLS? Well, it's an acronym, for Transport Layer Security. And this is really the new name for SSL, which was the Secure Socket Layer. Though I say new name, it's actually been called TLS since 1999. So that's now 20 years old. It's old enough to drive and go to school and drink and things like that. But people still call it SSL. And the two terms are really pretty much interchangeable. It doesn't really matter, but TLS is the proper name. There have been several versions of TLS through the years. SSL version 2 and 3, there wasn't a 1. Then in 99, TLS version 1 was released, followed by 1.1 not long after. And then in 2008, TLS 1.2 came along. And then finally last year, TLS 1.3. And 1.3 was quite a big set of changes. And it was really a pretty important thing, and it needed to be done because the last version was 10 years previously. So what's in TLS? Well, it's a set of standards for security and encryption and establishing encrypted connections between servers. It's a specification, really, so it's not actually a thing in itself. It's for other people to implement in libraries and so on. And you can wrap it around any higher level protocol. And most often that's HTTP is HTTPS, SMTP in various different ways, FTP, but note that's FTPS, not SFTP, which is an SSH-based protocol and completely different, and other things like IMAP and so on. There are some popular implementations of TLS. The most popular really is OpenSSL, and that has a long history behind it. One of the problems with OpenSSL is that it's very old. It's got a huge amount of legacy stuff in it, support for operating systems that no longer exist, and lots of legacy craft and lots of things that are insecure and broken. And a few years ago, there was a very public vulnerability called Heartbleed, and that was really down to just a bug in OpenSSL. And at this point, everybody realized that more or less the entire infrastructure of the secure internet was based on two people working in their spare time. This is really not a very good situation. And as a result of that, it got a whole load of sponsorship. But one of the other reactions was that it was forked a couple of times. And probably the most interesting one is LibreSSL. And this was done by the OpenBSD people who are responsible for things like OpenSSH and lots of really sort of definitive, secure ways of doing stuff has originated with OpenBSD. And what they did is they took OpenSSL and they just cut out all of the craft. They just threw away vast amounts of it. And the first few days of their changelog on the Git repo is really quite funny. Because they were just being really aggressive and they're just slagging off all this old code, and it's quite a funny read. Anyway, so LibreSSL is very much cut down, and you'll find that installed in quite a few Linux distributions already. Boring SSL is essentially Google doing more or less the same thing. They cut it down to really quite a limited subset. And the reason they called it boring SSL is because the idea is that you will never read a headline about boring SSL. So why do we want to use TLS? Well, fundamentally, it provides the trinity of features that we expect from a security layer. Provides confidentiality so that it can only be our data can only be seen by the people we intend it to be seen by. That we can prove its authenticity. We can be sure that the person that we're talking to is the person that they say they are. And also, we can vouch for the integrity of the data once it's got from one place to another. And there are various tools in it to help with that. Why we might actually use it on top of the stuff that we take for granted is you get better performance because it means you can use HTTP2. Google will rank you higher in search results. So that's kind of getting to the point where it's not really a different differentiator anymore. It's required for the backends for iOS applications. And some things have become dependent on TLS independently of the standards themselves. So for example, in Chrome 50, they disabled geolocation over unencrypted HTTP. And you might find there are various other little pieces of the kind of JavaScript environment that disappear if you're not using a secure connection. Fundamentally, though, it's all about keeping the wicked witch out, keeping the bad guys away from your site and away from your data and away from your users. So TLS is, it's kind of a framework into which things plug. The framework itself really is the protocol, and that hasn't changed enormously, though we'll go into the significant changes that have happened recently with that. But fundamentally, there are these sort of utility functions that sit within this framework and are used as part of the connection process. And these are really ciphers, MACs, and hashes. Hashes are all about the integrity. Some people refer to them as one-way encryption because the idea is that you can put in any amount of data, whether it's a single byte or a terabyte, it doesn't make any difference, you get the same size output. And the tiniest little change in the input will result in a completely different output. So this means that it's a very good way of identifying whether a transferred piece of data has actually remained intact and hasn't been corrupted in transit. So you can take the hash at one end, transfer it, can compute the hash again at the other end, and if they're the same, then it means you don't have to go through the file and compare them byte for byte, because that would mean that you have the two copies in the same place for a start, or an awful lot of additional network traffic. So hashes are very useful things. There are a whole bunch of hash algorithms, ones that you'll have encountered in particular, things like MD5 and SHA-1. Those ones I've marked as crossed out because they are considered broken and obsolete and you shouldn't use anything. So search your code base for the term MD5 and get rid of it. Replace it with something better like SHA-2. Now, there are different hash algorithms for different purposes. Now, MD5, SHA-1, SHA-2 are all about speed. They're intended to be as fast as possible and to give you a nice, reliable result on a very large amount of data. You can do gigabytes per second through these hashes, and they will be really quick. But there are other hash functions like bcrypt and argon2, which are aimed at password hashing, and TLS has nothing to do with that. So TLS does not concern itself with password hashing. That's dealt with in other places. If you're using PHP, probably the best place to get those functions by themselves is actually in libsodium. A step beyond a hash is a thing called a message authentication code. And this is very much like a hash in that you put in some data and you get a fixed size output. But it adds a key as well. So it combines the original data and a key to give you the result. Now, one of the important things about that is that, say for example, you're using your hash to try and suggest that the file that somebody has downloaded hasn't been corrupted. So you might publish your file, and in the same place you might publish the hash of the file. But if somebody's been able to hack into the server and replace that image file, then they can also replace the hash because they just simply recompute the hash and save it into the hash file, and nobody's any the wiser. But if you've used a Mac, they can't do that because they don't have the access to the key that you use to create the Mac. So it gives an additional layer of authenticity to the hash result that you've computed. The actual output looks identical. You can't tell whether something's a Mac just by looking at it. You have to know. The most popular algorithm really for creating MACs is actually a thing called HMAC, which is the hash-based message authentication code. And that takes a hash function like MD5 or SHA-2 and wraps it in an algorithm which adds the key to enable you to do that. There are some things that are not based on a hash, like for example Poly1305 is a relatively recent MAC algorithm, and that's not based on a hash, that's a pure MAC function. One of the problems with a Mac is that although it gives you this additional layer of authenticity, if you're going to be able to actually check and verify that this file has not been tampered with, then you have to have a copy of the key as well. So you effectively kind of moved the problem to somewhere else. And if you want to solve that properly, you really need to look at digital signatures, which is another way of using TLS, and it can do that, but I'm not going to cover that today because it just ends up being too much. The thing that everybody thinks about when we talk about TLS and encryption is, of course, ciphers. and ciphers are encryption algorithms. And the purpose of these is to transform data in a mathematical way that's hard to reverse without the key that was used to do the forward transformation. And these are based on sort of classical mathematical problems, such as factoring very large integers and the discrete logarithm problem, and more recently on elliptic curve functions. You can further divide up these ciphers into whether they're symmetric or asymmetric. Now, this is actually a very important distinction. A symmetric cipher is one where the same key is used to encrypt and decrypt the data. And that's something that you would probably want to use if you were encrypting things locally. Now, prior to the 1970s, all encryption was symmetric. And there's a basic problem with a symmetric algorithm is that somehow you've got to get the key from one side to another without the guy in the middle seeing it. You can encrypt some data and transfer it, but then the person at the other end can't decrypt it because they don't have the key. And similarly, if they try and return something to you, then you can't decrypt it. In sort of late 60s, early 70s, some of the security agencies on both sides of the Atlantic, in the US and the UK, actually effectively invented asymmetric ciphers, whereby you actually have two keys. You effectively use one to encrypt and one to decrypt, but they pair in this very neat way. But the net result is that you're able to transfer, to use the other person's public key, which can literally be public and viewable by everybody, but you can encrypt a message using that then only they can decrypt using their own private key. And that's a really neat trick, and it enables some very useful features in TLS. One of the other differences between symmetric and asymmetric ciphers is that on the whole, asymmetric ciphers are really slow, often thousands or tens of thousands times slower than symmetric ciphers. And so you don't want to use them all the time. However, what you can do is combine the two. And this is a really handy thing called key exchange. And the idea behind key exchange is that you use an asymmetric cipher to transfer a key, and then you can switch to using a symmetric cipher, which allows you to then switch to the much faster algorithm available through the symmetric cipher. That's a really handy routine sort of approach that TLS uses and HTTPS uses throughout. Cipher algorithms typically also broken into block and stream functions, like the AES algorithm that's very popular is a block cipher, and the char-char-20 cipher is a stream cipher. And the only difference really is whether it operates on a block of data at a time or a single byte at a time. Typical algorithms, RC4 and triple DES are now considered broken and you shouldn't use them. AES is very popular. It's quite CPU intensive. But as a result of that, Intel have built instructions into their CPUs to give you hardware acceleration for AES. And if you have hardware acceleration, then that's the fastest cipher to use. But if you don't, char-char-20 is actually much faster. And in software, it's about 3 or 4 times faster than AES, so that's worthwhile. The RSA cipher is kind of showing its age, but is still used. Although the RSA key exchange mechanism that goes with it is actually no longer supported. So what's new in TLS 1.3? Well, I mentioned we're getting rid of all the weak and legacy stuff. The idea behind TLS 1.3 is they wanted to really kind of clean house in the same kind of way that LibreSSL did. They want to do that kind of thing, but actually in the specification itself, so that all implementations follow that approach. So they got rid of lots of old stuff. And the net result is that, one of the problems with the earlier versions is that there were all these different options. For example, there's a cipher called null, which doesn't encrypt. It's just plain text all the way through. And so yes, it's encrypted using the do nothing cipher. This isn't very useful. And the thing is that when you get something complicated and unfamiliar to a new developer, say, and they go in and they're using this library and they go, ooh, which one of these shall I use? And I don't know what all these funny acronyms mean. I'm going to pick that one. And they might pick something which is completely inappropriate, broken, too weak, whatever. The idea behind TLS really was to get rid of all those situations and make it that they only allowed the strong stuff. So essentially, there are no weak algorithms remaining in TLS 1.3. They may, of course, get broken in future, but that's not a problem yet. There's more encryption in general. The point in the connection process after which encryption is applied happens earlier than in earlier versions of TLS. There's less overhead, which I'll get into in a minute. It supports something called perfect forward secrecy. If you imagine that you've encrypted something using your private key and you send it across a network, and that traffic is intercepted by some man-in-the-middle attacker who then scoops up all this data and just saves it, takes it away, spends the next 2 years spinning up thousands of AWS instances because they've got some evil government backing them, and eventually cracks your private key. If they have that private key, they can then decrypt all of your traffic. That's a really big problem. And that's the situation when you have a lack of perfect forward secrecy. What forward secrecy does is adds a random string to your key initialization, and this means that your private key isn't used directly. It's combined with this random string, and that random string is only used for the duration of that TLS connection. Once it's done and you've finished with it and you've stopped using it, it's never used again. It's very important that it's never used again. The net result is that if somebody does manage to decrypt that particular block at some distant future time when we've got computers that can do this in 5 minutes, they can only do that on that particular piece of data. They can't decrypt everything else. So it really reduces the attack surface on a very kind of long-term basis. Perfect forward secrecy is available in earlier versions of TLS, but in 1.3, all of the ciphers support perfect forward secrecy, and in particular the key exchange process all of them support perfect forward secrecy. Elliptic curve ciphers, the thing that's nice about elliptic curves, like the CHA-20 algorithm, is that they're very small and very fast. They're extremely efficient. They are available as an option in TLS 1.2, but they're there as standard in 1.3. There's also a really neat trick that's actually partly combined with the forward secrecy thing, this downgrade protection. Now, say you have a TLS 1.3 client and a TLS 1.3 server, but you've got a man in the middle. The initial connection between the two, we'll get onto that in a moment, it sends out a thing saying, these are the list of ciphers that I support. It's possible for the man in the middle to interfere with that and say, so if the client says, hey, I can use TLS 1.3 and this nice strong cipher, or I can use TLS 1.0 and this really rubbish old cipher that you can break in 2 minutes, they can potentially intercept that request and remove that option from it so that the server receives it and goes, oh, well, we better pick this low-quality cipher then. That's called a downgrade attack. But TLS 1.3 has a neat trick to the random string, which is used to provide perfect forward secrecy, contains a little bit that isn't random. And it's only set by clients that have TLS 1.3. Now, the man in the middle must convey that thing, otherwise the connection won't work at all. So they can't interfere with that. But if they have, if this string is present, it means that somebody has attacked the connection. And so it means that you can detect that you've got somebody trying to downgrade your connection, so you can just deny it. So we mentioned this handshake thing. How does it work? Well, I'll go through the two mechanisms in 1.2 and 1.3 just quickly. So first of all, the client says, hi, I want to establish a secure connection. Here's the list of ciphers that I support. And it sends that off to the server. And we're going to say that takes, say, 50 milliseconds on a good day. So the server receives that, and it says, OK, I'm going to choose this cipher out of the list that you gave me. So hopefully you want it to choose the best one, the strongest one. And I'm going to give you back my public key and the certificate and the signature to prove that I am who you think I am. So it sends that back to the client. The client goes, great, here's my public key. They have a default key that's just generated by your browser. And then it says, I've now finished. Sends that back to the server. The server goes, right, I'm finished as well. The client then goes, right, here's my HTTP request, now that we've established all that, and it sends that in, and then the server calculates that through PHP or whatever, and returns it back to the client. So we've got 3 complete round trips in order to establish a new TLS connection. That's really quite a lot of overhead, and that's one of the things that TLS 1.3 seeks to address. So, what's different in 1.3? Well, to start with, it just sticks more stuff into these initial handshake messages. Because the public key is public information, there's no harm in putting it in the initial unencrypted request with the client hello. So we've got the cipher list and the public key at that point. So that saved us one little trick. So the server receives that, it picks the cipher suite in the same way, it shares back its own key, certificate and signature, and it says, I've finished. The client says, I've finished too, and here's my HTTP request. So the server can receive that, send it back to the client, and you've lost a whole round trip. So that's a 33% improvement in latency, which is really worth having. And as we'll see, this is the kind of the worst case scenario for TLS 1.3, where you're having to establish a new connection from scratch. This is effectively the best case scenario for TLS 1.2. So there's just been a shift in the latency and overhead with 1.3. So once we've established a connection, we can then reuse some of this information because we know what cipher suite we're using. We've already got the keys, so we don't have to transfer those things again. We can just reuse them the next time that particular client wants to connect to us. So this time, because we've already connected, we have a session ID or a ticket. And the difference between an ID and a ticket is the session ID is just like a session cookie. It points at a store on the server side, which stores the information about the settings that are being used by that particular client. Now, there's a scalability problem there. Anytime you've got lots of clients that involve storing stuff on the server, you're just going to eventually run out of space on the server, even if the things are small. So what you can do in the kind of the memcache style is to offload that responsibility to the client. And that's what a session ticket is. So instead of storing that information on the server, you store it on the client, but it's encrypted by the server. So the client can't interfere with it. It can't be tampered with, and you know then that it's safe. And what's more, it's scalable. Every time you have a new client, they provide the additional storage for that ticket. So then the server goes, that's all cool. I know who you are. I know your settings. So I'm all happy with that. We're finished. The client says, I'm finished too, and here's my HTTP request. So the server receives that, processes that, and sends it back to the client. So here we've saved a round trip relative to a starting from scratch connection. How does this work in 1.3? Well, there's a big bonus in here. In 1.3, the client hello includes the session ticket, the key share, and it includes the HTTP GET request as well. And it's important that it's a GET, as you'll see in a minute. So the server receives that, here's my key share so that you can decrypt my responses, and I finished, and and I'm going to include the response to your request. And that means that we've actually got no overhead. This is what they call zero RTT, which is 0 round trips in addition to what you're doing on an unencrypted connection. So this really, with TLS 1.3, it's actually possible to get to the point where there's actually no latency overhead to using TLS. And that's a pretty big win. When you combine that with HTTP 2, as we'll see again, this all adds up to really a pretty considerable advantage. But there's a caveat here. It's that HTTP GET. The thing is with this, remember we were talking about the perfect forward secrecy and having this additional factor that's randomized each time. The thing is that here we're doing the same request over and over again. And so we should limit ourselves to GET requests because they should be idempotent, if you're familiar with this sort of REST terminology, that a GET request should never cause a change of state on the server side. So no matter how many times you issue your GET request, you should get the same response. And because we're effectively going to be reusing our perfect forward secrecy random element, it means that it's subject to replay attacks. So someone can, even if they can't actually read the data, they can capture it and replay it back to the server again. But if we make it that doesn't matter, then this isn't actually any kind of security risk. And there are even some tricks that some people have just published just back in February where they claim to have solved this problem, which is quite handy. So how do we go about creating a certificate so that we can actually set all this up and have it work? Well, first of all, we need to create a public-private key pair so that we can use that for our asymmetric cipher to do our key exchange. And that needs to be at least 2048 bits, and because that's a requirement of HTTP2. And we use that to then create a certificate signing request. If you've ever done one of these, whenever you want to go and create a request for a new certificate, it'll ask you questions like what the domain is, who the owner is, what country it's in, and so on. It just asks you a series of questions. And you fill those things in, and the result is this thing called a certificate signing request. It's not a certificate itself. You then need to have that signed. The CSR itself has a signature, and that must use SHA-2. Most of the certificate authorities around now will reject anything that's using anything less. It used to be common to use SHA-1 there, but that's not accepted anymore. So you need to get this CSR signed in order to generate a public certificate. So who are you going to get to sign it? Well, you can sign it yourself, and that results in a thing called a self-signed certificate. And that works perfectly well, and all the encryption is as strong as any other certificate, except that, of course, you could be anybody and nobody trusts you, and nobody should trust anybody in these circumstances because there's nobody vouching for you. You're just going, yeah, honestly, I'm really me. You've got nobody vouching for your identity. So the alternative is that you get it signed by a certificate authority known as a CA. So how do CAs get their authority to do this? Well, you have a thing called a certificate chain. Browsers and operating systems, so this is all on the client side, typically, have a store in which they save, or they have preloaded a whole bunch of root certificates. Now, these root certificates are actually just simple self-signed certificates. It's just that they're ones that we have specifically chosen to trust. We say, the people that build the browsers want to do security assessments of the CAs, and they go, we want to be sure that you're following these rules about how you issue certificates, which things you sign, how you protect your keys, and so on. And if they're not sure of those things, they'll get dropped. And that's a really sort of life-threatening thing for a company that's actually acting as a CA. So they need to make sure that they don't do any of those things. And it's happened. There have been quite a few CAs in the last few years that have gone down for various reasons. There was one called Startcom that didn't reveal that it had been bought by a Chinese company, and that resulted in them being dropped from essentially all browsers. Now, the server has a copy of those same certificates, but they're not really used at that point. On the server, we install the site certificate that we obtained from our signing process. So we've got the certificate for our site. But usually the site certificate itself is not signed directly by the root certificate. The root certificates are really precious things, and they have, or the private halves of them are. The public parts are all just public. So the CAs don't want to risk the exposure of actually having stuff interact directly with their root certificates. And so what they do instead is they use these extra things called intermediate certificates. And all that an intermediate certificate is another certificate that has been signed by the root itself and contains an additional authority that says you're allowed to use this key for signing other keys or for other certificates. So then the site certificate is signed by the intermediate, and this is why when you go and get a certificate, it typically has 2 files or 3 files. You've got your private key, the public certificate for your own domain, and then you'll usually get another one as well, which is belonging to whoever your CA is. And then in turn, that intermediate certificate is signed by the root certificate that the user already has in their browser. So this establishes the chain of trust between these things. And so effectively the root certificate is vouching for the intermediate, which is vouching for your site. Now, it's possible for an intermediate to actually be signed by more than one root certificate. And the reason for doing that is that it can be difficult to change this list of root certificates. It takes time to get these things distributed into operating systems. And Let's Encrypt had exactly this problem when they were trying to get themselves established as a CA, and they were actually signed, or what's called cross-signed, by 2 root certificates from 2 different other CAs. until they could get into a situation where they could actually become a CA properly themselves. And that's now happened, but in the early days of Let's Encrypt, they were cross-signed in this way. So long as that meant that so long as the client had one of these two certificates, it would work. So when we've deployed our certificate onto our server and the client connects to us, say our certificate lasts 2 years, its expiry is set for 2 years in the future, say something happens, like the CA gets hacked and their private keys exposed, you get your server hacked and your private key exposed. It would be useful if there was a way of telling or assuring the client or telling the client that that certificate should no longer be trusted. So if for example, if your certificate is stolen and deployed by some hacker on some other server, you want to be able to stop them from doing that. And the way that you would do that is you would tell your CA and they would revoke that certificate. But then the problem is, how does the client find out about this? Well, what it has to do is go and ask the CA. But you can imagine that there's a problem here. If every time you connect to a website, you also have to connect to the CA's website, that's a massive amount of overhead for your own site, but it's completely overwhelming amounts of traffic for the CA. So that's not really sustainable. The way that they look things up is this protocol called Online Certificate Status, or OCSP. And that specifically checks the status of your certificate with your CA, but it adds that overhead. But what you can do is a neat trick called OCSP stapling. And the idea here is that when you restart your web server and you've deployed a bunch of new keys, you can go and get the OCSP response from your CA directly, and you do it for your site on your server. And you might think, well, surely that means that you can just lie. Well, you can't, because that response, the OCSP response from your CA, is signed by them, and you can't fake that. So it means there's no harm in doing that. These OCSP responses are typically short-lived, maybe a few days to a couple of weeks before they expire. And so you don't need to renew them very often, but your web server will just take care of that for you. And Apache and Nginx have all this just built in. You just need to tell it to use it, and it will go and use it. And what that means is that when you do that TLS handshake, it includes the OCSP extension in TLS that provides that additional reassurance. And that means that the client can be sure that the certificate they're seeing hasn't been stolen, hasn't been revoked, and is still something that they can trust. So you need to get this certificate from your CA. One of the things that has largely gone away, thankfully, is that they have these different validation levels. DV, OV, and EV. And these stand for domain validated, organization validated, and extended validation. And the EV thing is what gave us these green titles in your address bar. Now, the idea behind it was that a CA needs to establish not only that they've technically signed your thing, but that you really are who you say you are. And so they'll often require extensive paperwork and record searches and often signed letters from lawyers and judges and doctors and things like that in order to establish and prove that you really do own this company and that company really is the owner of this domain. However, they kind of undermine themselves that by charging more for this service, but then actually reducing the amount of checking that they really did. So they were increasing their margins, but lowering their quality. It ended up getting to the point where it really actually wasn't worth it. And the other thing is that despite these green things in the address bars, they found that users just ignored it. They really didn't care. As long as it had a little padlock, they were happy. And so now the messaging in most browsers has switched. And now it will just warn you if stuff is not secure. It doesn't really care how you've secured it, because no matter which of these validation levels you've chosen, the actual encryption that it uses is absolutely identical. There's no difference in the encryption applied with a DV certificate versus an EV certificate. So basically, don't bother with EV. DV is just fine. With domain validation, the only thing you have to do is prove that you technically own the domain. And that's typically done by being able to serve a carefully formed HTTP response when someone makes a request to that domain, or, for example, putting something in your DNS. So essentially, if you're in the position where you can place content in specific pre-identified places on your web server, or that you can alter your DNS, they go, yeah, you've got to be the owner, because otherwise you wouldn't be able to do that. Inside your certificate, you can have some extra features that work nicely together. One of the extensions for TLS is this thing called SNI, which is Server Name Identification. One of the problems with the early versions of TLS is that during the TLS connection, it didn't actually know the host name. So it did all of these exchanges without actually any knowledge of the host name. So you might find that you do the TLS connection, and if you had multiple certificates, then it might pick the wrong one, and you wouldn't get a valid result when you tried to check that it was actually the domain that you were trying to talk to. So for a long time, there was a limitation that you could only have one encrypted domain per IP address. And that's really quite limiting, especially in the days of dwindling IPv4 addresses. So SNI allows the host name, the domain name, to be embedded actually down within the TLS connection itself. And that means that the server can then pick the correct certificate to deliver the response with. And that way you can have as many domains as you like and as many certificates as you like, all on one IP. This also goes nicely with this other feature called SAN, which is Server Alternate Name. Now, when you generate the CSR, the certificate signing request, which is how you go about getting the domain in the first place, you specify the domain that it's for. But it's possible to put multiple names in the same certificate. And the most common combination of that is to have, say, example.com and www.example.com. There's actually two separate names within the same certificate. Because otherwise you'll have problems. You end up having to redirect people only using an insecure connection, or you'll get errors because they've gone to the domain without the www on the front, or whichever way around you chose to do it. So there can be problems with that. So SAN solves that completely. You can actually just have long lists. I'm not actually sure what the limit is, but I've seen, I think, at least thousands of names in a single certificate. So that's a useful feature to have as well. You can also use wildcards, and this has another one of these little Trinity things. This will match anything, any string that's a valid host name dot your domain name. And you only have one certificate, and it will vouch for all of them. And this goes really nicely with wildcards in DNS and wildcards in virtual host definitions. It means that you can have dynamic host names that change all the time without having to touch any of your TLS, your DNS, or your web server config. It's a really great combination. Going back to the validation thing again, issuing certificates from a technical point of view is completely trivial. To sign a CSR, if you've got the root certificate's private key right there, is literally a one-line command in OpenSSL that takes a second. It's a completely trivial thing to do technically. But administratively, certainly historically, that's actually been the big problem. And yet, most certificate authorities actually based their pricing on the technical bit rather than the administrative bit, which was really not very clever. Startcom, which is the same CA that got dropped from all the browsers, actually was about the only one I've ever seen which priced things the other way around. They charged for validation, but not certificates. So once you'd established who you were, you could then have as many certificates as you like for no additional cost, because they're automatable and trivial to generate. But unfortunately, they don't exist anymore. Now, all of this overhead was really simplified a lot with Let's Encrypt. Now, Let's Encrypt, you've probably heard of it. It's a free CA. They will issue certificates free of charge, no cost at all. It's mainly backed by Mozilla, but there's a whole bunch of other companies behind it as well. And not only are they a free CA, but they also establish this thing called the ACME protocol, which is a specification, a standard for how to go about obtaining and renewing certificates. And that just allows you to automate the whole thing. Now, because of this, there's another security bonus, is that their certificates only last for 90 days, 3 months. So they're quite short-lived. But that's not a problem because they've made renewing them so easy. It's really quite straightforward. You essentially set up the renewal process as part of obtaining the original certificate, and you just set up a cron script that runs every day, and it just goes and renews all your certificates when they need renewing. And you can more or less forget about it from that point onwards. The old way of doing this was to have certificates that had long expiry times. And this came up, I think, just last year. This was a really good example of the problem of not making renewals easy. Ericsson makes lots of telecom-grade hardware that power lots of mobile phone networks. And 10 years ago, they installed a whole bunch of things for multiple networks around Europe, but largely in the UK. And on there, because they didn't want to address this need for renewing certificates, they used a TLS certificate that had a 10-year expiry time. So it was good for 10 years. And this hardware was installed throughout Vodafone's network in the UK. And all of these boxes failed at the same second. It literally took down the entire Vodafone mobile phone network in the UK for about half a day. It took out, I think, bits of Denmark as well. It was pretty far-reaching. It was a very big outage, and that was caused by an unrenewed TLS certificate. So make it easy to do this. Now, this last little thing I mentioned here, certbot. The ACME protocol, they say it's a specification, a standard, and people can then write implementations for it. And the certbot is a little command line application that implements the ACME protocol and is the official app to use for Let's Encrypt. But there are plenty of other implementations of this protocol as well. There's one that I really like called acme.sh, which is actually also their domain name. And that's a complete self-contained bash script with no dependencies. So it's really easy to deploy and very easy to run. And I find it's a little bit easier to work with than certbot. But certbot's fine. They're both excellent. So if you're deploying an application using TLS, how should you go about this? What are the things that you should aim for? Well, the most fundamental thing really is use TLS by default. It really keeps things much simpler. There's no ambiguity. Just encrypt all the things. Don't use protocol relative URLs. These are URLs that start with a double slash. They were kind of a bodge for when people had lots of mixed mode things, or where they had a site that could be accessed either with HTTPS or HTTP while avoiding these errors, what are called mixed mode errors. So say, for example, you load an HTML page over HTTPS, but the images within it are loaded from an HTTP site. Now, lots of browsers used to let you get away with that, but now it's quite likely they'll either not work at all or they'll spew errors at the user. Now, if the resource that you're loading isn't available over HTTPS, then you can kind of work around that by creating proxies, which you can do in PHP just with a one-line script. You should also make sure that your cookies have the secure-only flag set on them, and that means it's especially important for session cookies, so session identifiers, tokens, JWT tokens, and so on. You want to make sure that these things are not exposed over unencrypted connections. Now, we've described a lot of moving parts here. So how do you go about configuring a server to actually use these? Fortunately, lots of people have done this before, and Mozilla put together this nice little utility which builds TLS configs for popular web servers. So you go there and you just select which kind of web server you're using, which TLS library you're using, and what kind of target audience you're aiming at. You need to make sure that you redirect all requests to unsecured URLs to the secure versions. Use SNI to host multiple domains on one IP. Create your own set of Diffie-Hellman parameters for the forward secrecy thing. That's something that can take a really long time on a slow server, just so you're warned. But you only need to do it once or maybe annually. Use at least TLS 1.2 if you can, and disable any old or weak ciphers even within TLS 1.2. Make sure you enable TLS session caching and set up OCSP stapling for your root certificates. Beyond those things, there are a bunch of other things that you can do to improve security. You can add this HTTP strict transport security header known as HSTS, which is a way of telling your clients, we always encrypt. So if you've set this header on your homepage, which is delivered over HTTPS, and they see an image in the same domain, but that's not from a secure version of the URL, it will ignore the fact that it's not a secure one and actually just upgrade it automatically. on the client side. So that's a handy bonus. Now, one of the things about HSTS is that you can actually submit your domain to what's called a preload list, which is then used in the builds of modern browsers. And it then means that if your domain is in there and the browser knows about it before it's ever visited your site, it means that it will never ever make an unencrypted request to your site. And this avoids the problem known as trust on first use, which is what you have if you don't have that preloading. You can also add things in your DNS, a thing called a CAA record, Certificate Authority Authorization, bit of a mouthful. And essentially this says only these CAs are allowed to issue certificates for this domain. So if you're using Let's Encrypt, you might have, say, Komodo or something, or VeriSign. And you just list the CAs that you are intending to use. So you need your current one and any new one. Now these records are actually checked by the CAs themselves. If somebody makes a request to issue a certificate for your domain, they go and check in your DNS to see if they're on the allowed list. Otherwise, they will deny the request. Content security policy. There are whole talks on this header. It's really big and really complicated, but essentially it is a way of saying, I only want to load these types of media from these locations. So you can list the sources of your scripts, the sources of your styles, your images, your media content, whatever it is, your fonts. And that's particularly useful as a defense against things like cross-site scripting attacks, where you can prevent loading from bad sites. If you do TLS right, it means that you get to use HTTP2, which gives a big payoff. There's an RFC for it. If you're going to actually use it, there's a whole load of additional constraints. You've got to support TLS 1.2. You've got to support SNI. You must do PFS. You've got to have at least 2048-bit Diffie-Hellman parameters. You've got to disable compression and renegotiation extensions in TLS, which is something that used to be in old versions, but people found security problems, and you're better off actually letting HTTP2 deal with that compression. And that you must sign your certificates with SHA-2. If you do all those things, you can just enable HTTP2 on your web server, and it will just work. Once you've done all this, you want to test it, make sure it works. Well, the easiest thing to do is in your browser, when you visited the site, it'll have a little padlock in your address bar. Click it, and it'll tell you all about the certificate that's been presented, whether it's valid, when it expires, who signed it, what kind of constraints it has, which domains it applies to. You can see all of those things inside the certificate just in your browser, and anybody can check that. On a command line, you can do more or less the same thing using the OpenSSL S-client function. It allows you to extract certificates and so on. That's quite a useful tool. Much more easy to use is the Qualys SSL Labs tester. And this is something that you see pushed a lot. And it's a really good way of submitting your site to a whole bunch of different tests, and it will flag any, like for example, if you've allowed broken ciphers or weak hash functions and so on, it will tell you. To get your domain into the preload list that's built into browsers, you can just go and submit it to here, and it will do some checks to make sure that you're really going to do that before it allows you in. And there are a whole bunch of other places that you can use, particularly the observatory. TestSSL.sh is very much like the Qualys tester, but it runs on a command line, and you don't have to expose anything publicly in order to use it. So that's very good for internal testing. CSP, the site to use is reporturi.com, and securityheaders.com really just gives you an overview of more about the security headers in HTTP rather than anything further. And if you do everything right, you get these nice A+ grades. So just to finish up, this is the difference that doing all this makes. Okay, this is from webpagetest.org, which does a speed performance analysis on web pages. It's really good. Now, the first thing that happens here, this first request, you notice it doesn't have a little padlock at the beginning. It does an unencrypted request to the host name. So you can see the pink sections are TLS handshakes, and there isn't a pink section here because it's an unencrypted one. But we're getting a 301 response, so it's a redirect. So that's cost us 300 milliseconds before we even start doing anything. Then it makes the request for the home page, where you can see it's got a TCP connection in orange, and then it does the TLS handshake, and then it delivers the HTML. And then it has a follow-on bunch of resources, so we've got some CSS and JavaScript, and each one of those does its own TCP connection and its own TLS handshake. So if you add all those together, that's really quite a lot of additional overhead. This is also all TLS 1.2. Once you've done all those ones on this site, it then loads a bunch of other resources from other domains. And because there are other domains, you also get hit by DNS lookups, and then you get the whole TCP and TLS handshakes on top of that. So all of these add up, take quite a long time. Also notice the overall time, that's about 2 seconds to load that home page, which is not great. And there are sites that are much worse than that, but whatever. So the other thing you can see here is this is HTTP prior to 2. And you can tell that because otherwise these connections here would not be using separate TLS and TCP connections. One of the things about HTTP 2 is it multiplexes multiple connections and requests into a single connection. So you don't have to establish all those extra connections. When you do it right, this is one of my sites, you can see the first request is encrypted because we're in the preload list. Overall, the whole timescale is a lot shorter. We're at 0.7 of a second to finish loading, which actually means we actually finished loading before the other site delivered its first byte, which is, we like that. So we've got our DNS lookup, our TCP connection, and then notice that this little thing here, that tiny little bit of time, that's TLS 1.3 doing its thing. Also, this site is delivered over IPv6 only. It's another feature that may or may not help performance, I'm not quite sure. And then you can also see that we've got no additional connections. We've got no additional TCP connections, nor do we have any additional TLS connections because everything's coming from the same domain, so we have no additional connections to make. And all of those things added up ends up giving us a site that's effectively at least 3 times faster. And if you actually use the site, you find that it's actually really snappy and flipping around is really nice and fast. So in summary, TLS can be free of charge. It's faster when you use it with HTTP 2 because HTTP 2 doesn't work without it. Use TLS everywhere by default. You can take some simple measures to maximize security over the basics and fundamentally help Hansel and Gretel make it to your site safely. Thank you.